welcome to this explainer. Today, we're diving into the absolute foundation of nuclear physics. And honestly, we're going to completely reframe how you see the world, the objects around you, and literally the very concept of energy itself. You see, everything in modern reactor engineering, every safety system, every single megawatt of electricity flowing out of a nuclear plant, it all traces back to the physics we're about to cover right here. Get this foundation right, and I promise you, everything else we explore is just going to snap perfectly into place. Okay, picture this. Imagine you're holding a single grain of sand right on the tip of your finger. It's practically weightless, right? Barely even visible. Now imagine that one tiny grain containing more potential energy than a massive, heavy, 1-ton pile of black coal. It sounds totally like science fiction, but actually no, that is the literal reality of nuclear physics. The sheer density of the energy we're talking about here just completely defies our everyday human intuition. And once you understand exactly what's happening inside that tiny, tiny speck of matter, you're never going to look at the physical world the same way again. Section 1. The atom reimagined. A quick reframe. So let's kick things off by, rethinking basically everything your high school science teacher taught you about the atom. You know the classic diagram, right? Protons and neutrons just chilling in a cluster, electrons neatly orbiting around them like little planets. School probably taught you to think of the atom as this fixed, stable, permanent thing, just a quiet little microscopic building block that sits there doing absolutely nothing. Well, scratch that. Instead, nuclear physics asks us to picture this dynamic, incredibly tense battleground. The nucleus is actually held together by forces so unfathomably powerful, they make normal chemical bonds look like a polite, gentle handshake. The electrons on the outside, they handle everyday chemistry, but the nucleus, that handles nuclear physics. And man, under the right conditions, that immense hidden tension can be violently released. So the main players in this subatomic battleground are protons and neutrons. Now, as you probably know, every element on the periodic table is defined entirely by its number of protons. Hydrogen has 1, carbon has 6, uranium has 92. Simple enough. But here's where it gets super fascinating. Atoms of the exact same element can actually have different numbers of neutrons. And changing just the number of neutrons gives us what we call an isotope. So it's the exact same element, but with a different mass, and crucially, wildly different behavior. Let's look at how this actually plays out in the real world by comparing uranium-235 and uranium-238. Both of them have exactly 92 protons, which makes them perfectly 100% identical chemically. But U-238 is heavier by just 3 totally uncharged neutrons. Now, you might be thinking, what's the big deal? 3 tiny subatomic particles surely wouldn't matter much, right? Well, no way. That microscopic difference completely dictates how an isotope behaves inside a massive nuclear reactor. One acts as the primary fuel, while the other mostly just absorbs neutrons. I mean, the entire multi-billion-dollar enrichment industry exists literally just to separate these two practically identical isotopes. Section 2. Energy hidden in mass. Binding energy. Now let's zoom in even further to see exactly where the incredible, mind-blowing power of these isotopes actually comes from. Imagine if you took a proton and a neutron, weighed them completely separately, and then stuck them together to form a brand new nucleus. Something completely wild happens. The new nucleus actually weighs slightly less than the two particles did when they were apart. It's like the mass has quite literally just disappeared. But of course, it hasn't vanished into nowhere. Instead, it's been converted into an enormous amount of what we call binding energy. And Einstein's famous equation, E equals mc squared, tells us exactly how much. Because you're multiplying that tiny little bit of missing mass by the speed of light squared, which is a gargantuan number, that missing mass equates to a phenomenal burst of energy that's now holding those particles together. So when a heavy, tightly wound nucleus like uranium is struck by a neutron and actually splits to move toward a more stable state, it unleashes all that pent-up binding energy. And the scale of this? It's just staggering. A single fission event releases roughly 200 million electron volts of energy. To put that into perspective for you, a standard chemical reaction, like say burning a piece of wood or a lump of coal, that releases just a few electron volts per atom. So we're talking about a factor of millions here. That incredible 200 million electron volts is exactly why just a few kilograms of uranium can continuously power an entire modern city. Section 3. Navigating radioactive decay. Nature's instability. So the absolute crucial point here is that elements really, really crave stability. And when they aren't in a stable state, they try to fix it. And they do that through radioactive decay. Let's explore how. You might be surprised to hear this, but most of the 3,000 or so known nuclides in the universe are actually unstable. They're stuck in an energetically unfavorable state, and over time, they just spontaneously transform to find some balance, shedding energy and mass in the process. And they do this primarily through three main types of decay. Alpha decay ejects a heavy particle that's honestly so slow it can be stopped by a simple sheet of paper. Then you have beta decay, which shoots out an electron or positron. You'd need a few millimeters of aluminum to stop that. And finally, gamma decay. This is pure, high-energy radiation. No mass is lost here. It's just an excited nucleus dropping to a lower state and firing off a photon that requires dense, really thick concrete or lead to block.
Now, while we definitely can't predict when one single, individual atom is going to decay, we can predict exactly how a massive population of them will behave. We measure this rate using something called a half-life, which is just the time it takes for exactly half of a sample to decay. And the time span for this, it varies wildly. I mean, iodine-131 has a really rapid half-life of just 8 days, which is why it's a huge, acute, but short-term concern in reactor accidents. Cesium-137 takes about 30 years, making it a major long-term waste consideration. Meanwhile, uranium-238, that takes a whopping 4.5 billion years to have. That's roughly the age of the Earth itself, which, if you think about it, is exactly why we still have it in the ground today.
The sheer volume of these decays happening every single second is what we call its activity, and we measure that in becquerels. 1 becquerel is super simple. It equals exactly 1 decay per second. To give you a real sense of scale here, a freshly discharged nuclear reactor fuel assembly has an activity measured in petabecquerels. We are talking about quadrillions of decays every single second. It is so incredibly active, and it's emitting so much intense radiation and heat that literally just standing next to it without proper water or lead shielding would be absolutely lethal in a matter of seconds. Okay, let's see how this all builds up in practice, because decay rarely just stops at one single step. When a really heavy element like uranium-238 decays, it turns into thorium-234. But guess what? Thorium-234 is also radioactive, so it decays again and again, cascading down this really complex 14-step chain. It's constantly shedding alpha and beta particles, moving from one unstable element to the next, until it finally hits a stable element that no longer needs to decay, which in this specific case is lead-206. So you see, when we're dealing with nuclear waste, we aren't just managing the original fuel. We're essentially managing this entire cascading family tree of radioactive isotopes. Now, nuclear engineers don't just sit around trying to memorize all these crazy chains. They track them visually using what's called the chart of the nuclides. Picture this massive grid, where the horizontal axis tracks neutrons and the vertical axis tracks protons. Literally every known combination has its own little square on this board. Engineers plot paths diagonally and downward across this grid, watching elements decay step by step until they finally land in the safe zone. This safe zone is a curved band running right through the middle, beautifully known as the Valley of Stability. It's basically the ultimate treasure map for navigating the subatomic world. Section 4, From Physics to Power, Reactor Engineering. Finally, let's zoom back out for a second and connect all these invisible subatomic rules to the gigantic, real-world engineering of actual nuclear reactors. What I find truly fascinating about this is how every single abstract physics concept we've just talked about directly dictates how we actually power our cities. The fact that isotopes like U-235 and U-238 behave slightly differently, that entirely drives a massive global enrichment industry. That 200 million electron volts of binding energy released per fission, that single fact entirely drives the unmatched economics of nuclear power density. And those wildly varied half-lives we discussed, they completely dictate our real-world strategies for long-term radioactive waste management. Physics isn't just abstract theory here. It is the absolute, literal blueprint for the engineering. As we wrap up this explainer, here are the core foundational terms you really need to lock into your memory. Make sure you understand the difference between an isotope and a nuclide. Remember the massive, mind-bending power of binding energy. Know your alpha, beta, and gamma decay modes and what shielding they need. Grasp the concept of half-lives and becquerels to measure activity. And lastly, try to visualize those decay chains constantly moving, cascading down toward that valley of stability. These are the fundamental tools you need to really master the mechanics of nuclear physics. I'll leave you with one final thought to ponder today. The next time you look at a grain of sand, a piece of metal, or honestly any seemingly ordinary object around you, What do you actually see? Do you still just see a boring, static, permanent block of matter? Or do you now see a tense, incredibly dynamic universe of unimaginable hidden energy, just waiting for the exact right conditions to be released? Keep that perspective with you. And as always, keep learning.